We are also streaming and recording, so I guess that's okay by you, right, Pastor?
Yeah. I'm seeing some message from Zoom that this is being live streamed.
Yes.
Okay, got it.
So whatever you say will be preserved for posterity.
Okay.
We'll just wait for a minute just to see if.
Yeah, no worries.
Santosh, if Shomak joins, make him also a co-host.
Sure, sir.
Because he may join and then we will have him handle the questions if you want this thing.
Sure.
Thanks.
So you're doing all the IUCAA Colloquium online now? Or?
Yes, ever since about last 2020, April or something like that, I forgot now. It's been so long.
Yes.
We used to have it every week, and then now we are having it every alternate week. But it's also interesting that we can get everybody on. Okay, let's begin. It's great pleasure to welcome Pascal Notre Dame to our online colloquium. Pascal is a well-known person for people who have been in IUCAA much earlier, and he was even here as a postdoc with Sri Anand, 2009, 2010. And I think one of his children was also born in India, and that's a different story altogether. And Pascal then moved to Chile, and then for some time, and then he is now, for a very long time, for the last 11 years or so at ISO, is an extremely productive scientist. Some famous papers written with Anand, all on hydrogen, molecular hydrogen, atomic hydrogen. And today he will talk to us about both neutral and molecular absorbers in the environment of quasars and something to do with feedback. Pascal, please take it on. Thank you.
Well, thanks a lot, Kandu, for the presentation. So for me, it's really an honor to give a colloquium to IUCAA. As you said, I spent a year there. Yeah, 11 years ago. It's a long time now. And so at those time, I was working mostly on the neutral absorbers, molecular absorbers. And now the topic of this talk will be to get closer to the environment of quasars. So of course, I will start with some introduction about the gas around quasars and then move to my main talk. So this is work that I have not been doing alone. There are many people involved, and two of them from IUCAA, so Anand and Niraj. You can see the picture there, and also many other people around the world. So I cannot list everybody, but I put my main collaborators there. So the outline will be first an introduction about gas in and around galaxies. Then we talk briefly about quasar absorption spectroscopy, how it works. And then I will go into these two parts. So the first part about intervening absorber, and then the last part about proximate absorbers, which is the main topic of this talk. So we all know that gas is a key component of the overall population of galaxies, and it plays a very crucial role at all scales. And this you can see in the left figure, which is a simulation, where you can see that gas is expelled from the galaxies and is also accreted to the galaxy. So it plays a role in the building up of the galaxy and in the enrichment of the intergalactic medium. But when you look at the galaxy itself, you can split the gas in different phases, and two very important ones, which I will focus on today, are the atomic gas and the molecular gas. So these are the three maps that you see on the right. So the atomic gas here is a map, a real map in 21 centimeter emission. And then the middle map is again a real map of a galaxy, nearby galaxy in CO emission. And the last map shows the H alpha emission, which basically trace the star formation. So we see that there is a direct correlation between the molecular gas and star formation, and little between the atomic gas and star formation. So the gas has to go through different steps from outside of the galaxy, inside the galaxy, conversion, change its physical state, and then go to star formation. And all these processes involve very small scales, since as we know, stars form in molecular clouds, which are parsec size, while the picture here on the left, the simulation, shows tens of kiloparsec sizes. So to make a very short picture of this, we have the gas that feeds the stars. And this ability of the gas to feed the star depends on the physical and the chemical properties of this gas. And the other way around, the effect of stars onto the gas, this is what we call the feedback. And this feedback has many aspects. It can be UV field, injection of mechanical energy from supernovae or so, metal enrichment, etc. And all this will influence the physical and chemical properties of this gas. And then we have this loop. It will change the property of the gas, which will change its ability to form stars, and so on. So it's a bit complex interplay. And I do not pretend to explain all this, but to have a snapshot of what's going on. If we look at massive galaxies also frequently harbor supermassive black holes, which can be active, in which case is called active galactic nucleus. And in that case, the gas also plays a role in feeding the supermassive black hole, enable its ignition and making it shining. And then the very strong energetics around this black hole from the nuclei here makes a feedback onto the gas. So this is called the Aegean feedback. So here we see that gas plays a role in normal galaxies without Aegeans, with this loop with stars. And on the other side, in massive galaxies, it also plays a role with feeding of the black hole. And finally, the gas not only plays a role in feeding all this, but it also witnesses what has been and what is going on, since its properties depends on this feedback. So to study the gas in the distant universe, the best way till now is to use quasar absorption spectroscopy, because this is sensitive to all phases of gas and it's not dependent on the distance of the object. So this is illustrated here in this figure. So you have the quasar here on the left side, which you have the host galaxy in the picture B, and in A, at the very center, you have this very bright nucleus, which lights is so strong that it can reach the telescope several 10 gigayears later and recorded at the VLT or some radio telescope. So when the light crosses gas, which is intervening, which has nothing to do with the quasar, then we can probe the overall population of galaxies, which is dominated by small galaxies, regular galaxies, and a small fraction of active ones. But of course, the light starts from the quasar, and it also probes the quasar environments. And by the quasar environment, I mean the immediate environment of the shining source, but also the quasar host or the group, because quasars are in massive galaxies and they reside typically in groups. So we can also probe the galaxies which are nearby the quasar host. So for now, for the first part of my talk, I'm focusing on the intervening absorbers. And for this, you can ignore everything which is happening here at the quasar side. We just consider this as a bright point sources very far away. So the quasar, if we were there, we could take a spectrum. It would look like the spectrum on the left, where we see a broad continuum that shines at all wavelengths. And here, this is a Lyman alpha emission, which I represented here. When it is recorded at a telescope, then you see the right spectrum, where you see all these small little black lines here, which are due to gas in the intergalactic medium, which is called the Lyman alpha forest. And when you cross a large amount of neutral gas, then we see what is called a DLA, so damp Lyman alpha absorber, which is here seen on the spectrum as a big dip. And this is a trace of the neutral gas. So the historical definition of DLAs has been put because it was a detection criterion, which is that its equivalent width reaches like 10 angstrom or so. But coincidentally, it also matches the regime when the gas starts to be self-shielded and predominantly neutral. And if you look on the right figure, so I'm sorry, the axes are quite small, but on the x-axis, you see the log of the surface density of gas, and on the y-axis, you see the log of the surface density of star formation rate. And the DLA column density is here shown by this red line, and it is the density at which basically star formation starts to be consequent. So in the last years, the number of DLAs has been increasing tremendously, and in particular thanks to the Sloan Digital Sky Survey, which is this telescope here. And you can see here the number of quasars that have been observed at since it started, so in the 2000. So now this plot should be updated a bit, but it has been steadily increasing. So now we have 500,000, or a bit more than 500,000 quasar spectra. And from then, about several tens of thousand DLAs have been detected at redshift between 2 and 4-ish. So about this intervening system, I will just summarize here 3 important results before I move to the quasar environment. So one important thing when you have a survey of absorbers is to count them. So to make a census of how many systems you have. And this is represented in this figure where you see basically the number of systems against their column density. So the blue here are very numerous. These are the Lyman alpha forest. And the DLA, so neutral gas, corresponds here to the green end of the H1 distribution function. So since we have so many DLAs, now we can zoom into this region and have very detailed information about the shape of this distribution. And this shape, as I said, it's very sensitive to the consumption of gas by stars and the feedback effects. So this is an important result. It also says that DLAs basically contain the bulk of the neutral gas in the universe. So when you integrate this function, you get the cosmological density of neutral gas, and you can follow its evolution with cosmic time. So this is represented in this plot. So DLAs from the Sloan are here in the black, and then you have different tracers at lower redshift and in the local universe as well. So here what you see is that we have basically a slow evolution of this cosmological density of neutral gas. But what is important is that there is not enough neutral gas to account for the number of baryons in stars today. So the number of baryons of stars today would be somewhere here outside this plot. So this means that star formation has to be compensated by accretion of gas from the intergalactic medium that becomes neutral inside the galaxy. So it's quite interesting that just by counting DLAs, we can already say that there is a relation between star formation rate and the accretion rate of gas. The second important result is the chemical enrichment. So this neutral gas system, DLAs, have also many metal lines that you can see here in this plot. This is a stack of Sloan spectra. So you see many small lines from different metals. And then we can measure the enrichment of the gas. And this is shown in this picture where you see the metallicity of these DLAs against their redshift. So basically we see here that there is a steadily increasing enrichment of the gas chemical enrichment as a function of cosmic time. So we go closer to redshift 0, you go closer to now, and then the gas get more and more polluted. But we also see that there is a very large dispersion between different points. And this shows that the chemical enrichment in one place of the neutral gas can be very different from another place. This is quite interesting. We'll see later why. And the last main, I would say, result it's the physical state of this gas. And this is something that has been developed in particular with collaborators from IUCAA. So in the local universe, and theoretically, we can measure the different cooling and heating rates of the gas. And this is represented in this figure. So you have the heating rates, which are the dashed lines, and the cooling rates, which are the solid lines. But basically, we can say that the heating is dominated by photoelectric effect of the UV photons onto dust grains, and the cooling is dominated by line emission. If you equate all this, you make the thermal balance, then you get the phase diagram, which is shown here, with, for a given pressure, external pressure by the gas in the galaxy, you have three solutions. One is unstable, but then you have two solutions, one about warm gas and one cold gas. So for a given pressure, typically you have two phases of gas, one which is warm and with low density, and one which is cold with high density. And this cold gas allows the formation of H2, and then the formation of other molecules like CO getting denser, and then cascade into the formation of stars later on. So this is extremely important to know how much of this cold gas there is in the high redshift universe, and how this will get into stars ultimately. So this have been observed. And for this, we use mostly two tracers. One is an optical tracer, which is a H2, which can only form in the cold gas. And the other one is a radio tracer, which is a 21 centimeter absorption, which is sensitive to the temperature of the gas. So there has been huge observational effort with the VLT and GMRT, and now also with MERCAT, to which IUCAA is strongly involved. So the main result that we have a low covering factor of H2 and a low covering factor of 21 centimeter absorption. So basically, it's only 5 to 10% of the gas, of the line of sight, that crosses cold gas. So to summary, basically what we know about intervening DLAs. So we know that DLAs trace a gas blindly. They must accrete gas from their surroundings to sustain the star formation. They typically have low metallicity, but with large intrinsic dispersion, and we always see metals, so there is always some level of star formation. And then a small fraction of DLAs contain cold and molecular gas. So how can we understand this when you compare to our own galaxy, where we see cold and molecular gas everywhere? So the first thing that it is a cross-section selection. So you select the gas which has the largest area on the sky. So this means that we have typically large impact parameters, low pressures, and if you have low pressures, then you have small cold neutral medium fraction. And indeed, if you look at the galaxies which are responsible for these absorption systems, so this is something that has been evolving very much in the recent years, thanks to very efficient and sensitive spectrographs. We see the impact parameters between the centroid of the galaxy and the points where the gas is probed by the quasar line of sight as a function of this column density. And we see that at the impact parameter are typically large for most of the column density range, and only get small of a few kiloparsec at the very high end of the column density. And at the same time, I showed here in this picture the GRB DLAs in red. So GRBs are, it's the same principle, but the difference is that the source is inside the galaxy because it's a GRB itself. So by nature, you build with small impact parameters mostly. So the simple model to understand what we know now about DLAs is that we have warm neutral medium when at large distance from the galaxy where the pressure is low. And in the center of the galaxy, more closely, we have a mix of warm neutral medium and cold neutral medium. So typical intervening DLAs will only probe the warm neutral medium, far from the galaxy. So this is why you have large impact parameters. Extremely strong systems, which have a large column densities across the more closely to the center of the galaxy and have higher probability of hitting one of these very small cold neutral clouds, which have sizes of a fraction of parsec typically. And this is a GRB DLAs that explode in the center of the galaxy. I mean, it's in the optical region of the galaxy, let's say. And then you have also high probability of having high column densities and high molecular content. And then very quickly, we had cases where you have one line of sight which hits twice the same galaxy, with a difference between these two lines of sight, which is only about 1 kiloparsec. And we could separate the two lines of sight thanks to the lensing of this. So we can take a spectrum separately for each image. And for this, we also confirm this picture that the region here, where you see this cold neutral medium, is typically of kiloparsec size, at least. So you have one region which is kiloparsec size, but individual clouds are much smaller. So, okay. So if we get close to the quasar, now we'd like to understand what's happening for the same galaxies, but next to the quasar. So the main questions are, what are the properties of the gas in the quasar environment? Whether it is clustered, what are its kinematics, what is the chemical enrichment, and what is the influence of the quasar on the physical state. So this is basically the feedback processes. And how close to the quasar neutral and molecular gas can be because of this very strong shining source, which is extremely luminous, in particular in the UV. And then what kind of gas can we probe? Are we probing galaxies in the same group, the quasar host, inflow, outflows, etc.? So there are many questions when you get close to the quasar. So the first question is, how do you know that we are getting close to the quasar? Because when you observe a spectrum, the only information that you have, it's kinematical. So you know what's the velocity difference between your source and your cloud, but you don't know what's the physical difference. So it is generally considered that if you are at more than a few thousand kilometers per second from the quasar, then your cloud is very likely to be intervening, because this energetics it's too large to push. I mean, it's too large to be pushed by the quasar at these velocities for the neutral gas. But when you get closer, it could be both. It could be intervening or it could be associated. Intervening could be by chance, it is at this typical velocity distance from the quasar, but it's still a bit distant. So in that case, I call this cloud proximate. And this is what I will use in the rest of the talk. I'll call them proximate clouds until we have more information about this gas to know where it is. So the first large systematic survey for proximate DLA that we call PDLA, P for proximate, was done in 2008 by Spectroscopy et al. And they found about 100 of these systems. So you can say, okay, 100 is much less than the several thousands that we get for intervening, but this is in a very narrow redshift range. I mean, we're just looking close to the quasar. And actually, they found that there is a factor of 2 excess of proximate DLAs. So this is the black points here, compared to intervening DLAs, which are the gray points here. But from the clustering, because quasar resides in rich environments, you would expect a factor of 5 to 10. So their conclusion was that the neutral gas get ionized close to the quasar, and that's why actually we see a deficit of system. I mean, even if it is a factor of 2 excess, this excess is less than what we would expect it from clustering. So there was a study later by Ellison et al. In 2011. So we're not going into very details here, but you see as a function of velocity shift from the quasar, you see the equivalent widths of different metals. So here in 3 groups of proximate DLAs, all of them, the low column density and the large column density. But what we have to retain from here is that the equivalents are different when you are close to the quasar than when you are further away. So here, probably you're in the intervening regime, so gas which has nothing to do with the quasar. And here you have higher enrichment than typical DLAs, but it's also more ionized. As you can see, for example, the carbon-4 is much stronger here close to the quasar. So this is a screenshot of their abstract. And it's interesting, I highlighted here a few sentences, but mostly I would say that they say there is no evidence for Lyman alpha emission in the true of the composite spectrum. So they stacked all these proximate DLA and they don't see any sign of Lyman alpha emission, which I will show it's a bit surprising and probably due to a selection effect. So for this, let's consider the structure of the quasar. So the accretion disk, which emits most of the quasar light, is way too small to be resolved by any telescope. But what about the emission line region? So the broad line region is also in a very small region, and even the narrow line region it's very small and it's very far away. So we cannot resolve it with any telescope. But in the case of the Lyman alpha emission, the Lyman alpha can scatter very easily because it's a resonant line, and in that case, it can scatter up to very large distance, and we may see it, we may resolve it. So I draw here a spectrum. So I simplify the quasar spectrum. So you have the continuum, and here I just show the Lyman alpha line. And let's see what's going on. So if you take a spectrum, and then on the right side you have the image, like the narrowband image, which corresponds here to this pink box, you would see, I put a star here, but basically you see a single point, right? It's unresolved. And when you have a gas cloud intervening, you have a DLA, you absorb all this light from this single point, and the light goes down to 0. Now, if you look at the Lyman alpha emission, the Lyman alpha can be much more extended because it scatters away from the central region. And if I put the same cloud on top of it, you can see here that there is a lot of Lyman alpha emission that leaks and can still go through the cloud, I mean, on the side of the cloud. And in that case, the spectrum looks like this. So it's a weird signature. And since the first search for proximate DLAs, they were based on the total absorption, it's not surprising that you don't see Lyman alpha emission in this spectrum. And this is to show a first attempt by Finlay et al. In 2013, where actually we do find systems which have Lyman alpha emission in the center. So on the top 3 rows, you see examples. This is a Lyman alpha absorption, and you can see Lyman alpha emission. And to be sure, these are not 2 systems, one on each side of this emission. You can see on the bottom row, you can see the Lyman beta absorption, which perfectly matches here with this center. So in all these cases, you can see a strong Lyman alpha emission inside the proximate DLA. So here in this picture, I wanted to illustrate the fact that all this engine very close to the quasar can be very small, but the host galaxy itself can be much larger. And if this is in the distant universe, when you put a spectrum or slit or fiber or whatever you put on it, you will integrate everything. So you can also integrate other lines and continuum from the galaxy. And so even though most of the light comes from this very tiny region close to the accretion disk. So then there was another search, before going to the other search, this is observation of one of these systems with a somehow bigger telescope. You can see again here that there is this Lyman alpha emission in the bottom of this DLA that you can see here, and it's clearly confirmed with this bigger telescope here. But we also see that the carbon-4 is also not completely covered. You have here the absorption from carbon-4, and I skip the details, but basically you have some light here which is leaking. So the carbon-4 emission is also not covered by the cloud, by the absorbing cloud. And this observation also show that this Lyman alpha emission is extended. Actually, we do resolve it. And this is what you see here. This is just what is in the middle of the DLA. So what you see 0 here, it's absorbed by the neutral gas. And if you look at the 2D spectrum and you compare what you see from the continuum, so this is basically the seeing, and what you see from the Lyman alpha emission, this is a blue line, and you see that it is extended up to kiloparsecs, and that's why we see it in resolved from Earth. I mean, it's a few arcs, and it's larger than the seeing. So this means again that the leaking Lyman alpha emission does not necessarily come from the immediate active nucleus environment, but it can come from further out. It could be star formation, but it could be also scattering simply. So for this, Hassan Fatih Vazvari et al., they search for DLAs proximate to the quasar, but instead of looking for the H1 absorption, they look for the metals, so that you are not biased against those systems where you have strong emission. So they found many of them and separated in 3 groups: those with weak emission, with medium emission, and those where basically you don't see the absorption at all. So it's completely filled up with the Lyman alpha emission. but you still see the Lyman beta and all the other lines. So if you split into the three groups, they see more excitation of the gas when the Lyman alpha is leaking more. So this is what is illustrated here below. So those with no DLA, so with strong Lyman alpha, you can see that they have stronger, for example, silicon 2 star here, they have stronger carbon 4. So there is more excitation of the gas. So the interpretation is that these clouds close to the equator with high excitation are actually denser, smaller. That's why you see the excitation. And that's also why they cover less the Lyman alpha emission. But I will explain why it cannot be this case so simplistic. So this is basically their interpretation. So if you are far away from the equator, you have this neutral gas, DLA, typical. And if you're on top of the Lyman alpha emission, you have a very small cloud. But actually, whatever the size of this cloud, you would see this Lyman alpha emission. So are the clouds just more compact and denser in the quasar environment? So maybe this simple partial coverage of this Lyman alpha emission is too simplistic, because the size of individual cloud may not be directly related to the covering factor of possibly something which is extremely extended. So you have to take into account the filling factor of these clouds. It's not one cloud, but many clouds which will play a role. And excitation from the UV. Also, it's not only density that will excite the gas, and the overall relation between the quasar properties and the gas distribution, etc. So we have to move forward. And we need to better understand the physical and chemical conditions of the gas close to the equator, and we need to better understand the gas distribution and the quasar geometry. So for this, we went for another search of proximate system, looking directly for H2, so molecular gas, since it is very sensitive to the physical conditions. It's very interesting. And we could do a search without any prior on metals or the H1. So this is an illustration of the technique. Basically, we use the signature of the H2, which looks like a comb, and match this to the low resolution spectra. So this is an illustration of the detection procedure. So we have basically two criteria which are used: the depth of this line and the match between the expected profile and the dips in the forest. So these are examples of systems where we see here in the red profile, this is the H2 absorption. And if you look at the Lyman alpha emission from the quasar, where you have the strong absorption, we also see leaking systems. So here, or here, this is strongly leaking, but also systems where we don't see any Lyman alpha leaking through the absorber at all. So comparing approximate systems compared to intervening with the same procedure and the same spectra, and so we can clearly see already here that we have an excess of system with H2 close to the equator compared to the intervening, which is quite surprising, because we'd expect that the conditions close to the equator are so harsh that it is difficult to get molecular gas there. And this strong excess is also illustrated here. So here's the velocity difference with the equator. So if you go to the left side, you're going to the blue, so you're further out from the equator. And here you're actually moving towards the equator. This is a negative velocities. So this is an intervening background. So you would expect some number of system, which is some background here. But you can see that the proximate systems are very in excess compared to the equator. So now we don't have an excess of factor of 2, as shown by Prochaska before, but it's more like by a factor of 5 or up to a factor of 10 at the very close velocity to the equator. And this because this Lyman alpha emission in the center makes a bias into the search, the classical search of approximate systems. So here I show in this figure the fraction of photons which are leaking. So basically, this is the area of this emission as a function of its velocity difference to the equator. And we see more leaking photons when the DLA is closer in velocity space to the equator. So you see here, we have a small fraction of leaking photons. When you get very close to the equator, you have a large number of systems which large number of photons which are leaking. And then you get the other side, it also decreases. So how can you explain this? This could be completely observational. If you have a narrow spectrum and you look at the very narrow emission of the quasar, Lyman alpha, then it is very extended. But if you look at the wings of this Lyman alpha emission, the broad emission can come from closer to the nucleus. And then the Lyman alpha emission is less extended. So the narrow spectrally is more extended, and the broad spectrally is more compact, is less extended spatially. So if this is purely observational, it just depends on which region of the spectrum you're looking at, and it does not depend on the quasar or even the gas properties. Then we would expect that intervening delays also have this kind of partial coverage. We don't see it because it's not just absorbing at the right wavelengths, but you can look at other lines. And actually, we do see in some cases that there is partial coverage, like here by sulfur 2 lines at the very narrow emission line from the quasar. So here you can see, this is a zoom of this region, that the narrow Lyman alpha emission from the quasar is not covered by the gas. So a purely observational effect also works here. But there are signatures of physical effects, and these are the signatures of high excitation. Actually, those systems with the largest amount of leaking, I mean, with larger Lyman alpha emission, have also signatures of high excitation. These are the one which a red box here. They're all up here. So we have to move forward and to understand the physical conditions required for this molecular gas to survive close to the quasar. So this here, a very rude approximation of what is the density required for molecular gas to survive close to the quasar as a function of the distance to the quasar. So this is for two different metallicity. And you see that up to 0.1 megaparsec, you need density which are very high. I mean, 10 to the 3, 10 to the 4, compared to when you are here and you start to reach a background like intervening systems, where you can get density of 10 to the 2 only. So for this, bigger telescope help. That's why we went to VLT and got X-shooter observations of a pilot object. So I put pilot like this because it was just the first one in our list based on the RA, that's its J00. So our pilot object, it's shown here. So this is its X-shooter spectrum that goes from the UV to the infrared, and you can measure the extinction it produces compared to a typical quasar, and we found 0.4 magnitude, which is some dust, but it's not extreme as we can expect in other quasars. So with the X-shooter, we can also look at the specially extended emission lines. So we see here the oxygen 3 emission, and on the bottom, the Lyman alpha emission. So this is a bit complex, so I will take time. So this is a 2D spectrum. So you have the observed wavelengths here, and this is a spatial dimension. So you can see here broad emission like here. The white crosses are just skylines which are been masked. And when you go here to this region, you see emission on the top and emission on the bottom, though. Emission on the top, which is bluer, and emission on the top, which is redder. So if we subtract the nuclear emission, which is unresolved, the trace, then we get the picture on the right, and you can clearly see these two sides and two different velocities of the gas. And you can see it in the 1D spectrum as well. So the 1D spectrum, you see here the H beta line, and then oxygen 3 with a narrow component, which is the blue, and a large component, broad component, which is the orange. And oxygen 3, it's a doublet, so you see it repeated twice here and here. But when you integrate the spectrum only of trace out of the main region where you see the quasar, then you can see only the narrow emission. So basically, what do we see? We see a very broad, completely blue shifted and unresolved oxygen 3 emission, which is typically what we expect from nuclear wind, very close to the central engine. But we also see a narrow blue and red and resolved, I mean, on both sides of the trace, oxygen 3 emission, and which is more typically of galactic scale, because it has to go to kiloparsec size distances so that we can resolve it in two directions, and the different direction for the red and the different direction for the blue. For the Lyman alpha, we don't see emission on top, we see only emission in the bottom. But Lyman alpha is more complex because there is all this transfer, so I will come back to it at the end. When you look at the absorption line from the same spectrum, we see compared to these systemic redshifts that are completely blue shifted and with large range. So this is also typical of an outflow. And at the same time, we see excited species. So it seems like we are close to the quasar. There is something going on. It's not like intervening DLAs where you don't generally see this kind of lines like silicon 2 star. We have a very rich H2 absorption spectrum from which you can get many information about the excitation of the gas. And we found here, this is, so here on the left, you see the absorption spectrum. And on the top right, you see the excitation diagram. This is a column density as a function of the energy of the different rotational levels. So this kind of excitation diagram shows that it is highly excited. Typically, we would expect something going further down here, sorry. And what is interesting as well is that this high excitation of the H2 is not coincident with the excitation of silicon-2 star. So here you can see the silicon-2 profile. This is in the black, the silicon-2 star in the blue. But when you make the ratio of both, you see that where the red dashed lines are, this is where the H2 is, you see less excitation typically. So it doesn't seem that it is the same gas that is producing the strong silicon-2 excitation and at the same time producing the H2. So for this, to understand this, we have to model the physical conditions. So we went for cloudy. And I illustrate here the difference between modeling intervening gas and proximate gas. So in the case of intervening system, you can have different components and you can model them separately because you consider that the line of sight to the quasar here is just a probe. So it just measures the column density, but your UV field is due to somewhere nearby, I mean, from the galaxy nearby or the metagalactic background or whatever. While in the case of the proximate, the UV field comes mostly from the quasar. And then for each layer, you have to take into account what is transmitted through the previous layer. So it makes things more complex. But at the same time, what you measure as a column density here is exactly the column density seen by the cloud. While in the case of intervening, you assume somehow that the column density toward the quasar, it's the same column density that the gas sees, I mean, that the photon sees when they go through the cloud. So to simplify the problem, because you cannot put so many components, we started with only two, basically. So we split the gas into two clouds. So one is mostly responsible for the excitation of silicon, and one produces the H2. So we found that the silicon is mostly excited by collisions in ionized gas and warm neutral gas with density which are high, but not extreme. So it's like 10 centimeter cube or something like this. So this is what you see here. The white line is the observed value, and the rest and the red regions here are the results from the model. So you can see also that there is a solution with high density for the excitation of silicon, but this is at large distance. And if you put the gas at this large distance, then you have a mismatch in excitation and temperature of the H2, because this also pushes the H2 layer, which is behind, even further. What's interesting as well is that this excitation of silicon, which is shown here inside the cloud as a function of the H1 column density, can be very high here in the ionized gas. This excitation can be high, but this does not account for much of the column density, since the silicon-2 is not dominant here. So when you go into the neutral gas, so you pass the ionization front, then the excitation of the silicon star is less, but the column density of silicon-2 is higher. So overall, it contributes more to the observed column density. So this is a bit, you have to be careful with this. So for this single system, this is the configuration that we inferred. So the oxygen 3 line, narrow, which is blue on one side and red on the other side. So biconical like outflow. We have these clouds, the green ones, which are neutral, they can produce a silicon-2, and the red ones here, which are further out, where you can see the H2 absorption. And what is complex is what I said, the Lyman alpha emission absorption profile, which is also spatially extended. And this has been modeled using Lyman alpha transfer. Actually, this model here matches the observation. So here you see the data. This is a 2D spectrum, and this is the model. So at the same time, we produce the absorption, we produce the emission, the shift, I mean the red shift of this emission, which is mostly on this side on the red side of the centroid, and also the shift downwards. Actually, this is a bit complex overall, so you cannot say Lyman alpha is like oxygen 3. When it is coming towards it, it becomes blue because of this scattering. So only modeling can help confirming this configuration. So then we went for the dense molecular components and went for NOEMA observations for the CO32 emission. And this is what is illustrated here. We did detect the CO32 emission in that system. And this is very interesting. So when we compare to other systems from the literature, you have here the width of this line against the luminosity of this CO line. And our system is located here. So it has a very high luminosity, and it's also extremely wide, much wider than typical AGNs. I mean, other AGNs compiled from the literature, which are generally selected to be monsters in the infrared or in submillimeter, and compared to more typical AGN, which are selected from the X-rays, which are the orange points here. And here on the right figure, I show the infrared luminosity of the system versus here you have the CO luminosity. And here again, our point singles out. It's above most of the AGN from the literature, especially for its infrared luminosity. So here, all the systems in purple are again extremely extreme systems, are extremely luminous in the infrared systems. They are selected for this, or extremely obscured system. While here you see the submillimeter galaxies, which have typically higher CO luminosity, so higher molecular content for a given host luminosity. And our point looks more in between both and much higher than other ones which are selected for the X-ray. So if we put all it together, so what do we learn from this one single system? So the question is, does it trace early Aegean feedback? So first I will talk about what is here below, and then I move to the picture above. So about this Lyman alpha emission that we see in proximate DLAs and the fact that there is more excitation. So we have seen that there are both physical and observational explanations. So the physical, that we do see more excitation of the gas in the quasi-host compared to intervening systems. And we see that individual neutral and molecular cloud can indeed be much denser by a factor of 10 to 100 than in intervening system. And hence are much more compact and can have hundreds of AAU scale. So it's milliparsec scale, so extremely small clouds. But at the same time, our observations tell us that the Lyman alpha emission can be extended up to kiloparsec scales. So it is not surprising at all that it is not fully covered by an absorbing medium. So even in intervening systems, they do not cover necessarily this Lyman alpha emission. We just don't see it because we don't have lines there. But when we do see that this Lyman alpha emission is extended. And at the same time, we know that there are many studies now focusing on the quasar Lyman alpha emission using views, for example, and they always see very extended emission. So the fact that we see a correlation between the excitation of the gas and the Lyman alpha emission doesn't mean causality, because these individual clouds are way too small. So there may be something to do with the covering fracture, the filling factor of these small clouds into a medium, but it may just be also a correlation between the property of the gas and the property of the Lyman alpha emission with respect to the observed property of the quasar. So this is the third solution. This is a mix. So the properties of the absorbing clouds are related to the orientation and the evolution of the quasar, and so are the observed emission properties of the quasar. So one example, which you show with our pilot object, is that galactic scale outflows, they can carry dense clouds, but at the same time, they also facilitate the Lyman alpha scattering to large distances. And that's why you can see a correlation, not a causality between both. So putting it all together, the evolution scheme for quasars, that you have merging galaxies or dramatic events that go to a starburst regime where you have a lot of star formation, a lot of dust going on, so everything is obscured. And you first go through a phase where the quasar is red, which is mostly obscured. And this is where you see a lot of a lot of molecules. So for now, most of the radio observations, I mean, and submillimeter observations of CO system have selected these kind of quasars. They have been selected for being extremely red, extremely luminous in the infrared. And then they do see this CO emission. But in our case, a quasar was selected in the optical. It's a regular blue quasar with a little bit of extinction, not that much, but still it has this large amount of molecular gas with a very wide profile, which could be a post-harvest. I mean, the gas is still very moving everywhere, and that's why we have this very large emission. So basically, our system is the mix between this red quasar and the blue quasar. So what we inferred that the orientation of the system makes it appear as a blue quasar. So we have early feedback in the sense that the wind has cleared the way in one particular direction, where we see a little bit of H2, which is moving there with and highly excited, but the rest of the galaxy and the rest is still containing a lot of molecular gas. So we can see this early feedback just thanks to this quasar being orientated towards us. And this is the configuration that we inferred before. So with one single picture, we explain all the information, all the observations, the absorption, the excitation of the gas, the different emission lines, their spatial extent, and the radio observations of this large emission line. So to make progress, of course, we need a sample, and for this, stay tuned, because we have observations going on at both NOEMA and the VLT. And thanks a lot. I'm open for questions now.
Thank you very much, Pasquier. This is Shomak. I'm very sorry I wasn't there at the beginning of the talk. That was a fantastic talk, and with such colorful slides. And I'm very glad that you made this connection with the early feedback and this work. Fantastic. The questions, please raise your hand using the reactions button. Whoever wants to ask a question. Yes, we have the first question from Prakash. Prakash, go ahead. You're unmuted.
Thanks, Pasquier. Very nice talk. So I have a rather basic question related to this emission line. So you mentioned that the proximity DLA can absorb the emission line, the Lyman alpha emission. Consider the case where it absorbs completely. Then how do you determine the redshift of the quasar?
The redshift of the quasar can be determined from all the other emission lines. Mm-hmm. So for example, in this case where it's strongly absorbed, we determine the redshift not from the Lyman alpha, because mm-hmm. it's difficult, it scatters everywhere, but from the oxygen lines. So oxygen mm-hmm. 3 mostly.
Correct. And the other thing is because your continuum is now not very well defined, so your continuum fitting uncertainty would be much larger. So your column density estimates for proximity DLA, they would be larger, right?
Well, not necessarily, because mm-hmm. it's not only the Lyman alpha absorption which is fitted, but also the Lyman beta mm-hmm. first, and then okay, the continuum is obtained from using templates. Mm-hmm. So there is some uncertainty, that's true, but most of the constraint come from the very bottom of the line, so where the profile starts to raise, and this is not that sensitive to the continuum.
Right.
But yeah, it's true that especially from the Sloan data, and I mean, the typical error can be 0.2, 0.3 dex. That's true.
Yeah. The other thing is your model, simple model for proximate DLA. Do you make any assumption about the velocity of these clouds? Because if there is a strong inflow of the gas, then it can happen that they are not very close to the quasar, but because we are seeing in the velocity space, they appear to be very close to the quasar.
Yeah, actually it cannot be inflow, because we see the profile is completely blue shifted. Mm-hmm. But if you have intervening gas, actually, well, yeah, that's a good question. So if you have a gas which is intervening and that appears close to the quasar because of peculiar velocity, mm-hmm. then you would not see this excited species, and will not get this excited H2. So this is what we showed from the modeling. If you're far away from the quasar, we cannot explain at the same time the excitation of silicon 2, but there is also other species I did not show here, like the carbon 1 and the H2. So the full excitation diagram of H2 we cannot explain if you are far away.
far away. Yeah, thanks.
Actually, the distance here, we derived it's of the order of several kiloparsec, like 10 or 20 kiloparsecs. So we are talking about gas which has been blown up out of the quasar and probably even out of the host. And actually, the distance, maybe I can show it here. The distance we infer from the modeling of the absorption here corresponds to the typically distance that we see in the emission lines. I mean, the scale. So of course, one is transverse and one is longitudinal, but it's of about the same order. So we have like 10 kiloparsecs here, and we also have like 5 to 10 kiloparsecs here.
Dipanjan, go ahead.
Hi, Pasky. Very nice talk and lots of food for thought. So it's good that we are having evening snacks now. So a couple of questions, maybe if I can. One thing is regarding the distance at which you're observing this proximity DLAs. I understand you're saying that they are extremely compact, about a parsec or even less than a parsec. But how far are they from the quasar? Because if you compare the typical kind of molecular clouds we see in a galaxy, they are distributed all over the galaxy. But are you talking about the broadline region clouds very close to the quasar itself, like the torus or something?
No. In this case, because when you're going to Sloan data, we cannot say. We just have an idea. It can be close, in which case it has to be very dense, or it can be further out. But for this case, where we did the VLT observations and the modeling, we found distance of the order of 10 to 20 kiloparsecs.
Okay, so those might be the gas that's been kicked out.
Yeah, exactly. This is what we think. It's a gas that has been carried out by the outflow.
Right, and is a reason for and again, when you compare typical sizes of molecular clouds in a galaxy, they're usually tens of parsecs. Not well, you also have very small gas parcels, but you don't see extended clouds. You see very compact. At least your modeling infers very compact clouds. So could this be because the gas has been stripped out and then while during the outflow?
Yeah, this is a good question. Actually, one thing can be a selection effect. So if you cross a very big molecular clouds and so, you will just extinguish completely your line of sight. So when we're talking that what we see again along one single line of sight, you cannot be too large. You cannot have too large column density, otherwise you don't see the quasar at all. And from the CO emission, we know that there is a large amount of real molecular gas. So the fact that we see here very small clouds doesn't mean that there isn't very big and extremely large, gigantic molecular gas in there. The point that towards the nucleus and towards this line of sight, we don't see. So it has been cleared out. Let's say that it digs a channel into this molecular gas that we see in the CO emission, and digs a channel, and then the quasar appears to be blue, little extinguished, and with small column densities of H2.
Thanks, Pasky. Shomak, I have one more question, but maybe I'll just let Anand go ahead because he has his hand up.
Okay, I'll come back to you. Anand, question, comment.
This is not question. Just a comment that this geometry, now we have one more system, which is very interesting, that we are now detecting such objects in 21 centimeter. I think Neeraj may be around. We are seeing the same thing, very strong 21 centimeter absorption. And we have signatures of exactly like what Pasquier is seeing, low ionization lines, and Lyman alpha is beautifully present. So it's once again, it tells us that this is going to be exciting because we see the Lyman radio emission is up to 10 kiloparsec, unlike this optical source. So at some stage when VLBA goes up, we will be able to map this gas in front. Because see, that cannot be done now because Lyman alpha is providing a background screen to look at absorption, but it is coming from all over the place. Now we have VLBA images of sources which are beautifully resolving into different scales, and we are seeing the same system, right? You see cold gas, but it is not covering the broad line. I think this is a paper which we will be submitting soon in archive. Just want to make this comment.
Yeah, I just want to quickly jump in if I can, Shoma.
Yes, yes,
yeah,
super.
Yeah, so Anand, Pascal, I completely agree. But I find it still very fascinating the scale of outflows that this radio quiet quasar is producing, right? It's just completely radiatively driven in that sense. I think it with VLBI and everything also, it will be super interesting. But at the same time, I think if we can resolve the CO emission in that and look at those structure Pascal, that would be very exciting too.
Yes, it would be extremely exciting. And for this, I would like ALMA observations of the CO, and in particular to have it in two different lines, so that we can not only map the CO emissions especially, but also map the excitation of the molecular gas. But okay, we put a proposal on ALMA. It was rejected, unfortunately. So maybe next time. This is my hope. But yes, I agree.
Great. Yeah, that sounds exciting. I mean, let's go back to Dipanjan. Dipanjan, you had another question.
Just a short comment regarding, not a comment, a question. So this is regarding the blue quasar versus the red quasar thing. So this is a standard dichotomy that's been used in the literature quite often, and people really don't understand what is going on in this thing. So in the kind of technique that you and Anand and everybody are using, what can you say about the feedback budget? I mean, what amount of mass is being kicked out? And how is it related to the star formation rate of the host? Because of course, as an outflow is taking place, the star formation rate will not be instantaneously be affected. So you can have a blue quasar where there is an outflow of a young jet or a wind, but maybe not affecting the star formation rate. So can you comment on this regarding the feedback efficiency in the system that you're looking at?
Yeah, actually, unfortunately, from the absorption, we cannot have the mass of the outflow. So we could make some estimation if the column density is the same everywhere, and so, but it has really too much assumption. So I refrain from giving some number here. But again, this observed with ALMA, for example, if we could resolve the outflow in CO emission, then we could estimate more easily its mass.
Okay.
And then do all the energetics of the outflow. But we need more observations.
Yes, yeah, a plot like a KS plot of this kind of sources would be very, very interesting.
Yeah.
With ALMA and others. Thanks, Pascal.
Thanks, Dipanjan. Pascal, I had a very short question that's related to this. I mean, you very intrigued by the fact that you can actually, in some indices, make out whether the gas has left the system or been unbound. Now, as hierarchically galaxies grow, you expect that at high redshift, this is probably easier to do, even at the same level of outflows. So, do you see a redshift dependence of this kind of behavior? The fact that the gas can more easily kicked out of high redshift galaxies? Well,
not yet, because for this we need a sample. Actually, this is the very start of all this
even
research.
if
So it was yes.
Yeah, a nearby sample and a far sample and do a comparison and things like that.
Yeah, actually, all this what we selected in the absorption is all at high redshift. It's because we need this to be high redshift for the H2 lines to be observable from the ground. So we don't have a low redshift sample for now. Of course, we could mix with literature, but then we have to be very careful with selection effects. And yes, it's true that typically at low redshift, it's easier to study this red and blue quasar stuff and the outflow because you can resolve it. You can see it. While at the high redshifts, it's more indirect, and we actually will barely resolve. But you start to resolve this outflow. But yeah. This would be very interesting questions, but I think we need a few years before we can build up a sample and start looking into this.
Thanks very much. Thank you.
If I can just comment, Pascal, this sample which you showed for very bright quasars, the detection of CO frequently in that will give some input, right? Barely whatever Bischetti's sample.
Yes.
I know that it is extremely bright quasar sample. It may not be representative, but we know they detect very often, right? The CO flows.
Yes. Yeah, it's true. This these are monsters in a sense, but all the difficulties that you have this, if you compare the low redshift with the high redshift, then you have to be careful about your interpretation, whether this is due to evolution or if it's just selection effect, and the selection will change your orientation.
So it's mostly selection, I agree.
Yeah, so if you select this to be extremely red, and you may select also systems which are younger, but also systems which are not orientated towards us. So this is a peculiar thing about this one single system, that it shares both properties, and thanks to its orientation. So yeah, it's really not easy to disentangle evolution from orientation and selection effects. There is much work to do.
Thank you very much. I don't see any other questions. Kandu, did you have a comment?
No. I think pretty interesting.
Very, very interesting. Okay, so thank you very much. And Zoom applause for Pasquier. And so thank you very much for this very, very fascinating talk. And till next time, and we hope to see you here very soon.
I hope so. Thanks a lot.
Thank you.
Thanks, Pasquier.
Bye, everybody.
Bye.
Thanks a lot.
Do you have an announcement about the next colloquium, or when?
By Professor Tripathi.
That is 2 weeks from now.
Yes.
Okay. Thanks very much. Bye.
Bye-bye.
Bye.